Hello, today what we're going to talk about, just very briefly, are pH indicators. These are chemicals used that change color based on the pH, and this is sometimes a very useful thing to know. One that we discussed very early on was litmus paper, and what we're seeing here is a piece of blue litmus paper, and it's being touched to, I don't know if this is a grapefruit or what, it's a citrus fruit of some type, but you can see the blue turns red. Acid is what that means. Anytime the blue litmus turns red, that's an acid. If I were to put red litmus paper to the same piece of fruit, it would stay red, and you generally want to do both blue and red to verify the pH of a substance using litmus paper. Litmus paper is not highly precise. It won't tell you the pH is 3 versus a pH of 4. It will simply tell you that you have a pH of less than 7 or greater than 7. pH paper, on the other hand, changes beautiful colors of the rainbow, and pH paper will give you values, whole numbers, 0, 1, 2, 3, 4, 5, 6, 7, and so on. They also make pH paper that goes by half pH. So pH paper is very, very useful. This is maybe not the way you would use it, but it shows what's going to happen. You take the pH paper, and here what they're doing is dipping it into different solutions of ammonia and baking soda and so on, and you can see the color change. You would then hold a piece of paper up to the side of the container to figure out the pH. A better technique that doesn't use nearly as much pH paper would be to take a small square, maybe a 1 centimeter square piece, take a glass stirring rod that's clean, dip it into your solution of ammonia, and then touch that glass rod to the small little strip of paper, and you get the same color indication without wasting the material. Why do we like pH paper? Well, you might think it's new technology, but you can see it really isn't. It was invented around 1904. What's nice is it's actually made from several different chemicals, and each chemical changes color at a specific time. And so when you merge them together, you get all the different rainbows of color. So it's inexpensive, it's highly sensitive, it is accurate. There's a lot of reasons people like pH paper. There are other indicators we can use, and some of these indicators are man-made, some are naturally occurring indicators of acidity. I've listed a few here. Methyl orange will be red with a pH less than 3.1, and it turns yellow above 4.4. And sometimes you want to have that change right around 4. Methyl red, another indicator, will change in the range of 4.4 to 6.2. Bromethymol blue will be yellow below pH 6.2 and blue above 7.6. Bromethymol blue is one that we will use in lab when we have a strong acid and a strong base, because it changes its transition in the range of pH 7. Here's another one that we will use, phenolphthalein. It's colorless below pH 8, and then above pH 10, it turns red. We won't go beyond 13, so we won't have to worry about that. But this one is going to be used when you have a strong acid with a weak base, and we'll want to have it come out at a pH range of around 9. We'll discuss those indicators more a little bit later. So as it says on the bottom, bromethymol blue should be used if you have a strong acid and a strong base, because its endpoint is around pH 7. Phenolphthalein is if we're using a weak acid, such as acetic acid, and a strong base. When you add the strong base to reach the endpoint, you actually overshoot a little bit with the weak acid, and so you don't want to see when it's 7, you want to see when it's maybe in the range of, let's say, 9, and we'll describe why that is in a little bit. Methyl orange, if we're completing our thought, would be used for titrating a strong acid with a weak base. So you don't pick an indicator based on a color pattern that you like. You pick an indicator based on where it's going to show the proper endpoint for you. When I discuss titration in greater detail, I will describe what an endpoint is. This is showing lots of different indicators, and on the top would be the pH and what color they would be. So you can see they change colors. In general, the blues and purples are bases, and the reds tend to be acids. Phenolphthalein would be the exception to that. It tends to turn, it's colorless in an acid and then turns pink in a base. These are just showing you the transition colors with strong acid, strong base of litmus, red in an acid, blue in a base. Bromethymol blue, yellow in an acid, blue in a base. Green when it's right at the transition color. This will be another indicator that we will use in the lab, and we'll see that transition color in our titration. Phenolphthalein, colorless in an acidic solution, and it looks red here, but it's more of a magenta, maybe a pink, hot pink color when it's in a base. Phenol red is yellow in an acid, red in a base, and again, what we're looking at is where the pH transitions occur from. Okay, let me go back. So you can see bromethymol blue transitions right about pH 7, which is what we want it. Litmus paper transitions right about 7, so that's a good indicator for a strong acid, strong base. If you have a weak acid, strong base, I told you we want to be a little bit transition to be above 7, so we use these indicators here. And if we have a strong acid with a weak base, we want the transition to be more in the acid range. I would tell you which indicator you need to use. This is more for an advanced study if you were wondering why you choose one indicator over another. I'm not going to really discuss this slide. I'm just going to skip through it here. We'll just skip it because I'm not going to ask you this. This is the structure of phenolphthalein. If you're wondering, it has these two OHs on it, and here's methyl red and methyl orange. We'll discuss this little structure a little bit later, but for right now it's not important. Found some nice graphics for you, not that you care. And here are a bunch of indicators. You can see, depending on which indicator you choose, they will change color at a lot of different points. And this is how you can get pH paper to change colors from 0 to 14, just using a combination of different chemical indicators. Here are some edible indicators, in other words, foods that change color. Oftentimes you'll see chefs add acid to their dishes, and that's to create a sour flavor, but it's also to bring out and enhance the colors of substances. Blueberries, for instance, will be purple at about, pH 5, but if they're pH 8, they'll be green. You wouldn't want to eat them if they were green. They would tend to be a little bitter. If they become red, then they're going to be a little bit too sour. They're going to be, pH 3 or below. And so we can change the color of our food products by simply adding acid to the dish. Red cabbage is one that changes the colors of the rainbow over a wide spectrum. It's one that perhaps your middle school teacher or elementary teacher used to do a science activity. This is showing red cabbage. You will grind it up in a food processor, filter off the leaf matter and leave the liquid behind. Then depending on what you add to it, it will change red, all these different colors indicating the pH. So it makes a pretty darn good indicator. The problem with red cabbage as an indicator in the chemistry lab is when that red cabbage sits around too long, it starts to get smelly. And nobody wants to have smelly labs. So generally it's a cute little thing to do, but not done in real chemistry labs with red cabbage. I want to show you phenolphthalein. Here's the structure of it up here when it's acidified or in an acidic environment, and it turns pink when it's in a basic environment. So what happens in an acidic environment, this protons, this H here and H here, stay on the molecule. But when you put it in a basic environment, it feels it has to fight, so to speak, and it basically donates these protons to the solution, trying to neutralize the basic solution, and therefore it has an O negative, and then it has a conformational change. It also changes down here a little bit. Now what that means is instead of having this benzene ring where you have a double bond, single, double, single bond, it changes to make a double, single, double, single. In other words, electrons have moved. Anytime electrons move, you will see light. That's what causes light. So that's how phenolphthalein indicator works. When it loses that proton, it causes a conformational change. Again, I'm not going to go through these color changes with you, as I will not be asking you about those. We'll stop here. I just wanted to give you a very quick lesson on basic indicators, how they work, what they are. Hopefully that helps a little bit, and we will stop recording once I figure out where I need to be clicking on this silly thing here. Let's hit escape, see if that does it. That doesn't do it. That doesn't do it. That doesn't do it.